Okay, so uses of ultrasound. Remember that ultrasound is anything with a frequency greater than 20,000 Hertz. And the first thing you need to know about ultrasound is what we were talking about previously when we were talking about rays that can be transmitted and rays that can be reflected. So whenever there's a change in density, some of the light will be reflected, some of the light will be transmitted, or sound, or whatever kind of wave it is. Okay, as soon as there's a change in density, some is reflected, some is transmitted. What ultrasound can do is ultrasound times how long it takes for this wave to get back and how much of it gets back, and then it knows how far that. So let's say that this is an arm. Let's say this picture represents an arm, and you wanted to do an ultrasound scan of an arm. So you put a sensor here, it emits an ultrasound wave. The ultrasound wave goes through the muscle, so that's density of muscle. It gets to the bones, that's density of bone. Some of the ray is reflected at that point and gets back to this person and gets back to the sensor there. So let's plot a little graph of what that would look like. So it goes, okay, you send out your signal, you wait, you wait, you wait, you then get a signal back. Okay, that's the reflected wave. And this distance here, so that amount of time, sorry, so this is on the bottom graph here, that's time. And that time there, from there to there, that is how long it took the wave to go to the bone and back again. So if you remember, speed equals distance divided by time, but that's there and back, so that's 2D. So if you want to know what the distance to that bone is, it's going to be distance equals the speed of the wave in the muscle times by the time divided by 2, and if you want to divide by 2, that's the same as saying a half. So half times by the speed times by the time that it took. Okay, but some of that wave will continue in the bone and then get reflected back from the bone. So you're going to get another peak. And what that tells me is that, and then if you want to know what if you knew that there, that would tell you the time that it took the wave. So the total time here, that is the time it's taken for the wave to go from here to here, and the difference between the two peaks is how thick the bone is. So if you want to know how thick the bone was, you could use this to work out how thick the bone was by using a half of that time times by the speed of the wave in the bone times by the time. Okay, and then so on. Okay, now the other thing that you need to know is that the size of the peak, so the height of the peak, so the peak height is greater if the difference in densities is greater. Okay, so what we're saying is, so if I gave you the example, if you received a signal that looked like this, then you would know that a wave went in, it got reflected, and the time it took for it to get there and get back is this amount of time from here to here. But not only that, you'd also know that there's been a big change in density there, because you've gone, because it's come, whereas you know that when it's travelled to the next one, you know that the change in density wasn't as big because the peak here is less. And that's not to say that the density is less here than it is here. What it tells you is, it tells you that the change in density is a lot bigger here than it is here. And then here, the change in density is really big again. Okay, so if you were to build up an image of what that looked like, what you're talking about probably is, you're probably talking about something that's gone like air to metal to wood, to different types of wood, because these changes are really small. And then it's probably gone back to metal, and then back to air again. Okay, so what we're saying is, we're saying big change in density, small change in density, even smaller, big change in density again. Okay, and it doesn't matter whether it's going in or going out. The bigger the change in density, the more is going to be reflected, and the less is going to be transmitted. And remember that the time that you're measuring there is the time it took for it to go there and back again, which is why it's 2 times the distance. Why is ultrasound useful? Ultrasound is useful because it's non-ionizing, which means it's not dangerous. Okay, it doesn't cause electrons. It doesn't cause atoms to lose their electrons, unlike X-rays. So it can be used, which is why ultrasound gets used for babies. It can tell the difference. The computer can build an image of it, a 3D image, and it can tell the difference between the densities of the matter by how much is reflected each time. So you can see bone and soft tissue in different types of tissue, which a lot of X-rays will just go straight through soft tissue, whereas ultrasound you can actually start to have a look at soft tissue, because you can just look at the difference in the tissue. So all in all, very, very useful.